Okay, this lesson is for section 1.3 and 1.4, linear functions and models and linear regression. I'm also going to go over some problems from the lab manual and some nonlinear regression. So from the text in section 1.4, number 21, we have the following problem where we're talking about soybean production in millions of tons and cultivated area. So the independent variable is this top one, the area in millions of acres, and the dependent variable is the production of soybeans in millions of tons, because the production depends on the area. And we're supposed to obtain a regression line and show a plot of points together with the regression line, and then interpret the slope. So to do that, what you do is, I've just put here, this is x and this is y, and so my independent variable column is, sorry about that, area in millions of acres, and the y coordinate or dependent column is the production of soybeans in millions of tons. And so to do this regression line here, what you do is you select column A and column B, and you go to Insert, Scatter, Scatter with markers only, and then here you Chart Tools and Design come up before you hit Enter, and that's great because we want layout 1, and we can label our axis title. Just click on it once, you don't have to delete it, and it's up here, but when you hit Enter it'll go down to the x-axis, and then again on the y-axis that's production in millions of tons. So that's that. Okay, now what I'm going to show you how to do is to get this trend line here. So what you want to do, let me just delete it. Okay, what you want to do is pick a point, doesn't matter which point, but you want to hover over a point and then right click and then click Add Trend Line, and you have lots of choices. We're going to do a linear one, that's what it defaults to, and we're going to display the equation on the chart and display the r-squared value on the chart. And so there's our equation, and you can round, you know, in your head, or I'll show you how to change the rounding. So the way you change the rounding is if you right click on the equation, you'll get this Format Trendline Label, and then you want to go to Number, and then you can change to however many decimals you want. It's going to change it to 2. What's more important is sometimes we want to have lots of decimals so that we get a really good prediction. So that's how you change your decimals. Format Trendline Label. Okay, so now we have the independent variable x is area, the dependent variable y is production of soybeans. Okay, the second thing is to interpret the slope. Remember what slope is. Slope is the change in y over the change in x here. And so what you want to do is the number 1.62 is the slope because it's the number in front of your x, and you want to steal the units from the word problem. So our y is production of soybeans in millions of tons. So this is y over x, 1.62 millions of tons of soybeans. And you can make 1.62 a fraction by putting it over 1. And then your x units are area in millions. So 1 million acres of land. Okay, now they're both in millions. So we can divide out the millions. If we divide the numerator by a million, you get 1.62 tons. If you divide the denominator by a million, 1 million divided by a million is 1. So that's okay to do because what you did to the numerator you did to the denominator. So that's 1.62 tons of soybeans for every 1 acre of land. So to interpret, you're going to, for every increase in acre of land, your soybean production will increase by 1.62 tons. Okay, question 23. is about automobiles and motorcycles in Mexico. And in A, it says to let X be the number of automobiles in millions and Y be the number of motorcycles in millions. And we're going to get another regression line. So this chart has years, and then the second column is automobiles, third column is trucks, and the fourth column is motorcycles. Well, they're telling us to compare motorcycles with automobiles, so we're going to let X be automobiles, and we're going to let Y be motorcycles in millions. So I'm just copying these values down here, and then to create a trend line after you get the data typed in, we're going to select the two columns, insert a scatter plot with markers only. Remember, before you hit enter, choose layout 1. Just click once on the axis title. This is autos in millions. Remember, nothing will happen until you hit enter, and then it'll just change. And then Y is motorcycles in millions. Okay, so I've already done that, and we delete it. Okay, now what we want to do is create another regression line, and we're going to look at the correlation, the R value. So let me delete it. Okay, so this data does not look linear, but we still want to look at what a linear regression line would be. So we're going to click on linear, display equation on chart, display R squared value, and there we have it. Okay, and so the slope, again, I wrote it down here. Your slope is 0.0322, so over 1. Okay, that's step 1. Your Y, millions of motorcycles. Your X, millions of automobiles. Divide out the millions, and you get 0.0322 motorcycles over 1 automobile. And then if you want to manipulate this so that the decimal goes away or becomes, the number becomes bigger than 3/100ths of a motorcycle, what we can do is multiply this numerator by 1,000 and this denominator by 1,000, which is legal because you can multiply by 1. And so you get 32.2 motorcycles for every 1,000 automobiles. The denominator is your independent variable. So when I interpret slope, I like to say it this way. For every increase in 1,000 cars, there's an increase of 32 motorcycles. And it's increase because this is positive. So if one of them were negative, you would say something like, for every increase in 1,000 cars, there'd be a decrease of 32 motorcycles. Okay, then the R value, this is your R squared value here, 0.5989, which is here, and we want the R value. So if you take the square root of this, you'll get the R value. So you just type in equals SQRT and then parentheses 0.5989. I could and then hit enter, and then you get your R value. And an R value of 0.77 is not close to 1. Therefore, the correlation is not strong. And we could tell that because this straight line does not fit the curvature that's happening here with these data points. The next question is about New York City apartment housing costs from 1994 to 2004. And the problem says to let t equals 0 represent 1994. So what this is they've zeroed out the years. Instead of using the years 1994, they're letting 0 represent 1994 and 2 represent 1996. I'm a big fan of doing this because it makes the equation smaller and easier to deal with and less error. And so what we will do is we will type in this table here, and then what we want to do is select the columns with the data, and again you're going to click insert scatter with markers only, layout 1 so you can label, And you would have this here, except I didn't label. I could add the label here. Years since 1994 and price in millions. Okay, and so what we want to do is we want to create a linear regression. So we're going to right click on a point, add a trend line. There's linear, display the equation on the chart, and there is your linear regression equation. It has an r-squared value of 0.9476. And so then what you want to do is, this is the actual data, and this is the predicted. So this represents the actual price, and this represents the predicted price. So you want to create a column of predicted prices, and the way you do that, I'll redo it, is you type in the formula. This is what we call the model. It's a linear model. So I have equals 0.1264 times the independent variable, which is t, which is h5, plus 0.2229. Hit enter, and then click on the cell where the formula is, get your fill handle, and drag it down. And these are now predicted prices based off the linear model. So these are the predicted prices in millions. And I'll do wrap text there. And so the key here is, once you have the predicted prices, then this actual data really just is not used anymore. So if I ask you any questions, even if I ask you this question here about this 6 represents the year 1994 plus 6 is 2000. If I ask you what the price for an apartment is in 2000, you wouldn't use this actual value, you would use this value. So that's pretty strange, but that's what we do. Okay, so this is a linear model, and what's not good about this linear model is that there's some curvature in this data here, that it increased very slowly here, and then it's increasing at an increasing rate here. This line is increasing at a constant rate. So we need to check another model, and so we're going to go right click on the data, add a trend line, and there's choices here, and this looks a lot like a quadratic model with this curvature here. So there's no quadratic written, but it's a polynomial of degree or order 2. So anytime it's asked for a quadratic model, you want polynomial order 2. Display the equation on the chart, and there you have your quadratic model. And again, this is a very small a value, so you may want to go and right click, format trend line label, and go to number and take that out to 6 decimals, and that gives you a value that is carried out to 6 decimal places. And the r-squared value here is much better, 0.992075. Okay, so the quadratic model, again, you would type in the formula, and I have already typed in the formula without the decimals out to 6 places, and that's fine in this case. And then I'm going to drag it out. So these are the predicted prices in millions based on the quadratic model. So in 2000, the linear model says that apartments were $0.98 million. The quadratic model says that apartments were $0.88 million. And then it asks for residuals. Now, we're not going to be tested on residuals, but residuals are just the actual data values minus the predicted data values. So if I want to calculate the residuals for linear, what I'm going to do is click on the actual data, I5, minus the predicted data, J5, and then bring that down. The quadratic residuals, again, would be actual data minus the predicted, I5 minus L5. Drag that down. And we're not going to deal with residuals, but the residuals for the quadratic, if you were to add those up, they would be smaller than the residuals for the linear. What we're going to look at is R squared value, but not R squared value in first place. It's going to be in third place in the things that we look at. What we're going to look at is, does the model fit the curvature of the data? And you can see the quadratic is better. Second thing we're going to look at is end behavior. That's right here. Both of these models have the same end behavior. In other words, as years go by, apartment prices are going to go up. The quadratic, the model, as years go by, the apartment prices are going to go up at an increasing rate instead of a constant rate. And then the third thing we're going to look at is just which one is closer to 1. So on all accounts, the quadratic model is better. Okay, so now we'll turn to the lab manual, and if you go to the linear application section, I wanted to do number 1 with you. So number 1 is more like a 1.3 problem. It says a $15,000 robot depreciates linearly to 0 in 10 years. A, find a linear equation for the value as a function of time. B, how much is the robot worth 3 years after it's purchased? And so the first thing we want to do is we want to notice that this is a hint. This is function notation, and the wording tells you that they want time to be the independent variable and value to be the dependent variable. Value is a function of time. So that lets me know that what we have is time is years, t is time in years, is my independent variable, and v we're going to let be the value of the robot. And I call this little area that I'm writing down is my math English dictionary, and I think it's really important to take time to define your variables and to think about who the independent and dependent variables are. So since t is independent, v is dependent, the order pairs are all going to look like t for time first, comma, v for value second. So there is this line here that's going to give us 2 ordered pairs. A $15,000 robot depreciates linearly to 0 in 10 years. So that means when the time is 10 years, when 10 years have passed, the value is 0, and it has to be in this order, 10, 0. That's one order pair. And then the second order pair has to do with this robot is worth $15,000 as soon as it's created. So at the initial time, when time is 0, the price of the robot is $15,000. So that's 2 ordered pairs. And if you read section 1.3, it goes through how to write an equation. I'm going to show you how to do it with Excel. So TV, our time is 10 and 0. And our value at 10 is 0, and our value at time equals 0 is 15,000. And so I want to select these 2 columns. Notice that like usual, I put my order pairs in columns instead of rows. Excel has a little trouble with that you need to know about. When I try to create a line or a scatter plot, with 2 data points and they're vertical, Excel has trouble, and it thinks that this point should be 1, 0 and that this point is 2, 0. So it's just having a hard time understanding that there's 2 order pairs. It's really easy to fix. All you have to do after you do the scatter plot is go up here, and it'll show up switch row column. So if you just click on that once, it'll understand that you meant to graph the order pair 0, 15,000 and the order pair 10, 0. Okay, so easy fix, switch row column. Now we create a trend line, and it will basically write the equation for you. So the equation, and you can change this to function notation. I'll do that just to show you what you would write on your paper, because I told you to use the letters V and T. Well, I didn't actually, so you could use any letters you want, but function notation was requested. So V of T equals negative 1,500 plus 15,000. Okay, so now what we're going to do, as I stated before, this is my actual value, this is my predicted value, but since r squared is 1, of course, the predicted values, if I type in the equation, are going to be exactly like the actual values. That's very rare. That only happens when you have 2 points because something is not working right. Let me pause it. Okay, I had a text box hiding there messing me up. Okay, so I put the value in, I put the function in, see? And I'm going to drag it down, and I'm going to drag it down in empty space, and I want to answer question B, which says how much is the robot worth 3 years after it's purchased. So if I substitute 3 in for T, then it will be worth $10,500 3 years after it was purchased. Okay, so the next one is a little different, so I wanted to talk about that. Number 2, a city's population was 30,700 in the year 2000 and is growing by 850 people a year. We need to find a formula for the city's population, P, as a function of the years since 2000. So if we do our Math English Dictionary, it's saying that T, our independent variable, should be years since 2000, and P is a function. The population is our dependent variable, and you'll know the population when we know T. The other thing that I wanted to show you is that this isn't two ordered pairs here, although technically you could create two ordered pairs. A city's population is 30,700 in the year 2000. So if we know our ordered pairs are in this form, then one ordered pair is 0 years since 2000. The population was 30,700. And then it's growing by 850 people a year. That's a slope. 850 people is the same as population per year. That's the slope. So you don't need another ordered pair. You don't need Excel to do that for you, although you could add 850 to this value and 1 to 0 and get an ordered pair. But you've got y equals mx plus b in your back pocket. So P of t equals the slope, 850t, and then the y-intercept is any time your x-coordinate is 0, that's a y-intercept. So that's why you don't need Excel to write this equation. So there's your linear equation. And then to answer questions, you could just type in the formula, 850 times A11 plus 30,700. And then the population in 2010, you'd put 10 in. Now to answer question C, you're going to need to goal seek. And to goal seek, you would not be able to type anything in here, because if you type 45,000 in, the formula will disappear. So you have to go to Data, What If Analysis, Goal Seek. You want B12 to change to 45,000 by changing cell A12. And then I don't like it when people say that the answer is 16.82 years after 2000. I would really like it when people do the math. So the year 2000 plus 16.82 would be the year 2016.82. That's my preferred answer there. Okay, so the last problem I'll do is a data regression problem, and it will take some time to do because we're going to explore different types of models, not just linear. And so the years are 2005 through 2008, so I'm going to zero out my years and let my independent variable be years since 2000. And then the amount spent on Halloween is in millions. So I'm going to insert a scatter and go ahead and label. And this is an interesting little trick here, since I want to explore a lot of different models but with the same data. What you can do is click in this area here and then copy, and then click in an open area and paste and paste. I want to look at 3 different models. So the first model is a trend line. Right click on a point, add a trend line, and we have this model here, and it's got an R-squared value of 0.9, and this data is curving, but this line is perfectly straight. So that doesn't look like the best fit. Well, what does this model look like? You have to remember what different functions look like, and this could be quadratic. So I'm going to right click, add a trend line, and again, a quadratic is simply a polynomial of degree 2, and I'm going to try that out. And I hope you catch this. This is pretty tricky here. Look at this R-squared value. It's a perfect 1. That means that this is a perfect fit. But is it the best model? And the answer to that is no. Number 1, you want to look at the curvature of the data, and that's how I knew that this linear wasn't good. But number 2, you want to look at the end behavior and ask, is it realistic? So what do I mean by end behavior? Well, if we keep going with this quadratic, you have to know what a quadratic is going to do. It's going to go up and then it's going to turn back down. So if we use this model and we make predictions, then we are going to have predictions that say that as years go by, the amount spent on Halloween is going to start to go back down. And there's nothing in this data that says that that's going to be the case. This data is increasing slower and slower as we go, but not decreasing. So this fails the end behavior test big time. And so you don't even get to question 3, look at the R-squared value, because it fails the end behavior test. So quadratic is not a good model. Okay, so what else could we pick? Well, if we right click, add a trend line, we've got a couple of more. I'm going to click on them and you can see what this is going to be. This exponential is hard to see, but this is curving up when this data is curving down. The exponential is concave up when this data is concave down. So that's not good at all. But if we go to a logarithmic or a natural log, there's a concave down curve, and if you remember about natural logs, they kind of start to level off. And so that's pretty good. So let's go ahead and look at the R-squared value for this natural log. And we get R-squared value of 0.9382, and it's got the right curvature, and as years go by, the amount spent on Halloween is going to continue to increase, but slower and slower. So that's not a bad model. But there's one more I wanted to look at, and that is this power. Power functions also have the same concave down, kind of leveling off idea. So these 2 choices are pretty tied. They both have the right curvature. They both have the right end behavior. And so number 3 right here, now you can look at the R-squared value, and it's the tiebreaker. So according to this, your log model has a higher R-squared value, 0.9382, than your power model. So the best choice for this problem is the logarithmic model. Okay, so now that we have the right choice, we'll go ahead and put in our data. This is years since 2000, amount spent on Halloween. Remember, after we get our model, the actual data is not useful anymore. So I can put this over here in this area, but I have decided not to do that. So I'm going to just start at 1, and then I'll type in this log model. And remember, natural log, you just type in ln and then parentheses x, which is this cell. And the reason I put a 1 in here, if I don't put a 1 in here, it's going to give you a domain error, because remember, You can't have 0 in this spot in a natural log. So if I start with 1, then it doesn't give me an error. It does give me a negative value, but that's okay. I'm ready to make predictions. We want to find the output in 2010. So if I put 10 here, then we predict that $77.46 million would be predicted for Halloween spending. And then the next question, we want to know the year when 70 million would be spent. Now here's another trick. We've already defined amount spent to be in millions, so you would not want to goal seek to this number 700000000. You won't get an answer. You have to convert it to millions. How many millions is this? This is 70 million. So we want to goal seek this to 70. The other thing is you don't want to goal seek while you have an undefined. So let's just put the number 1 in here, and then now we can goal seek. And again, data, what if analysis, goal seek to value 70, not 70, 0, 0, 0, 0, 0, 0. That would give you an error by changing this cell. And then again, I don't want this answer. I want, this is years since 2000. So 2000 plus this answer gives me the year. So in the year 2008, we would predict $70 million to be spent on Halloween. Again, don't worry about this not getting to 70. Goal seek just stops when it gets close enough. Okay, so this is important enough for me to just review one more time. How to pick the best trend line. 1, look at the curvature of the data. 2, look at the end behavior. Is it realistic? Does the model support the end behavior that you would expect based on the given data? And another question you can ask is, does the model give you negative values when you should clearly have positive values? So the example I'm thinking of is, there's a population question where if you pick quadratic, it's going to go below the x-axis, and so for several years, the model would predict a negative population. So you don't want that either. And then the third thing, you want to look at the r-squared value. It can be the tiebreaker. So if I were to ask you on a test to give me 3 reasons why you picked the model that you picked, you would want to say more than, well, the r-squared value was close to 1. You would want to talk to me about the curvature of the data. You would talk to me about the end behavior, and then your r-squared value does need to be close to 1, but that's the last thing you look at.